Good evening. Welcome to this presentation. It should be of interest to novice geochemists. You will first be introduced to molecular orbital theory, and then we will see how it is applied to a certain kind of analysis of rocks which involves absorption of electromagnetic waves. In atoms, electrons revolve around the nucleus. When two atoms come together to form a molecule, their orbitals overlap and the electrons gather around the molecular nucleus. That is, the orbitals characterize the molecule as a whole. Electrons in an atom do not revolve around the nucleus, unlike planets which revolve around the sun. They have a region called the electron cloud in which they are likely to be found. For example, hydrogen's single electron could be anywhere within the green region shown in this diagram. The electron clouds are also called orbitals. Different orbitals have different shapes. For example, s orbitals are spherical shaped. This means that electrons in the s orbital can be found anywhere within the sphere. Also shown is that p orbitals are dumbbell shaped. This table partially lists the orbitals in the order in which they are filled. The electronic configuration of an atom can be deduced from this table. For example, this has been demonstrated for the elements silicon and nitrogen, but this can be done for any number of elements. When two atoms combine, they may exist in two states, bonding and anti-bonding. Placing electrons in the bonding orbital gives a species that is more stable than the isolated atoms. The antibonding molecular orbital has a higher energy than the orbitals of the isolated atoms, and the electron clouds of the two atoms are not in contact with each other. Sigma are a type of bond where the bond is symmetrical around an axis containing the two nuclei. This happens when the two electrons being shared are both from s orbitals. Sigma bonds are also created when two p orbital electrons overlap, such that the internuclear axis and the atomic orbitals are on the same line. So in this case, px orbitals will form sigma bonds. Pi bonds are symmetrical about a plane. They are created due to the overlap of p orbitals that are perpendicular to the internuclear axis. In the given example, the internuclear axis is in line with the px orbitals. They will form sigma bonds. The pz and the py orbitals, on the other hand, will form pi bonds. Each hydrogen atom has a single electron in its 1s orbital. They each contribute their electron to form a bond. The bonding electrons are filled first. The electrons sit in the bonding orbital, leaving the antibonding orbital empty. Since there are more bonding orbitals than antibonding orbitals, the molecule H2 is stable. Helium atoms have 2 electrons in their 1s orbital. To form a He2 molecule, first 2 electrons enter the bonding orbital. The remaining 2 electrons fill the antibonding orbital. Since the number of antibonding orbitals is the same as the number of bonding orbitals, molecular orbital theory predicts that He2 molecule cannot exist. Lithium is solid at room temperature, but molecular orbital theory correctly predicts that a Li2 molecule could exist in the gaseous state. Following the same rules as that for the hydrogen and helium molecules, we obtain an electronic configuration for Li2. There are fewer antibonding orbitals than bonding orbitals, hence Li2 molecule will be stable. When a molecule is subjected to energy, the molecule's electron may absorb the energy. The high energy state of the electron is called the excited state. The last electrons to fill the molecular orbitals usually enter the bonding state of the last orbital to be filled. When subjected to energy, the electrons jump to the higher energy antibonding state. The energy difference between the antibonding and bonding states of a molecule is fixed. A beam of white light is a mixture of light rays that have a range of energies from 1.65 electron volts to 3.26 electron volts. When such a beam passes through our molecule, some of the light rays which have energies that is exactly equal to the energy difference between our two states are absorbed by the molecule. The absence of rays of some energies turns white light into a colored light. The resultant color is the color of the molecule. This phenomenon of color due to absorption is used to identify some molecules. If we shine white light on a substance and find that the resultant light is missing the wavelength 500 nanometers, we can conclude that the substance has a molecule which absorbs light of that wavelength. This principle forms the basis of the working of an instrument called the UV visible spectrophotometer. Its use gained popularity in the 1950s with the development of what is called rapid analysis of silicate rocks. Previously, geochemists had to dissolve rocks, then precipitate out a salt containing the element of interest and then physically measure its mass using a balance. Suppose an analyst wants to determine the silicon content of a rock. They will crush and powder the rock sample. The powder will be attacked with molten sodium hydroxide. Once the mixture cools, water and HCl is added to the liquid. To this solution, many other chemicals are also added, the most important of which is ammonium heptamolybdate. Silicon forms a complex ion with the molybdate part of the ammonium molybdate. Under reducing conditions, this complex is blue in color. This complex absorbs light of wavelength 812 nanometers, which is in the infrared end of the spectrum. A UV visible spectrophotometer can be used to measure light of the near infrared region in addition to the UV and visible portions of the spectrum. In addition to the rock of interest, the experimenter also analyzes the absorption of two other rocks whose silicon content is already known. These are called standard solutions. The experimenter also analyzes a solution that contains only the reagents used in the analysis and no rock. This sample is called the blank. The values of the absorption of the sample of interest, the two standards, and a blank solution is plotted on a graph. The amount of light of wavelength 812 nanometers absorbed is proportional to the concentration of silicon in the solution. The blank contains no silica. It will have a small amount of absorption solely due to the reagents used in the experiment. The amount of silica in the standards is known and is plotted against their absorption. Once the absorption of the sample is known, its concentration can be found. In addition to silicon, many other major and minor elements can be analyzed using this technique. Here's a question to round out this presentation. When an excited electron leaves the antibonding orbital to go to the stable state of the bonding orbital, it has to release some energy. Can this energy be characteristic of the molecule? Hope you have fun chewing on that. Thank you.